In this screencast, we're going to work through an example problem involving the separation of two species, in this case acetone and ethanol, using distillation. And we're going to use the McCabe-Thiele method to do this. So I'll give you the time to pause this and read the question so you understand what we're doing. And in other screencasts, you can see how these operating lines and methods are derived. But in this screencast, we're just going to work through this problem. Now the first thing you'd want to do is collect vapor-liquid equilibrium data and plot the X versus Y, or liquid versus vapor mole fractions of the more volatile species. So in this case, we have pressure at 101.3 kilopascals. We have our mole fraction of acetone in the liquid and the mole fraction of acetone in the vapor plotted on this XY diagram. I also have an x equals y line that I've thrown into the plot. This will help us as we go through the McCabe-Thiele method. Let's go ahead and determine our feed line. So our feed operating is defined as y, the vapor mole fraction of acetone, is equal to the quality of the feed, Q, over the quality minus 1, times the liquid mole fraction, minus ZF to designate our feed composition, and this is over our quality minus 1. So what is our feed quality? Our feed quality is an indication of how much of our feed is liquid or vapor. And we could write this as a balance of our liquid flow rates in and out of our feed plate over the amount that we feed. And so when we look at this, we want to get an idea of what our feed plate is. So I've drawn our feed coming into our feed plate. We know that we have a vapor flow rate leaving, a liquid flow rate coming in. The vapor coming from the stripping section we designate V bar, and the liquid leaving the feed plate we designate L bar. And these flow rates are designated differently because we're not sure what the feed is. The feed could be some form of a vapor, or it could be some form of a liquid. Now in this case, we have a subcooled liquid. So we have no vapor that's coming in from our feed. And more so, some of the vapor actually comes in and gets condensed to join that liquid leaving. So we lose some of our vapor. So we would expect that our V, our vapor flow rate leaving the feed, is going to be less than our V bar. And so to determine this quantity, we need to write a balance and substitute the values we have into this. So we know L bar is going to be equal to L plus our feed, F, plus for every 6 moles of our feed, we condense 1 mole of our vapor. So we could say that it's also going to add 1/6 of our feed. We can use this information to plug into Q. This becomes Q is equal to F plus 1/6 F over F, and we get a quality of 7/6. We plug that in here. We know that our feed composition is equimolar, so we have a 0.5 mole fraction for ZF. And now we could write our operating line equation for the feed. So our feed operating line ends up having the equation y equals 7x minus 3. And so we could plot this on our XY diagram. So I've plotted my feed operating line. We can start working on our rectifying operating line. So our rectifying line has the equation y equals L over V, L being the liquid flow rate and V being the vapor flow rate in this section, times X, the liquid mole fraction, plus D, the distillate flow rate, over V times XD, which is the liquid mole fraction of our distillate. The other equation you may see is in terms of the reflux ratio R, which then has the form R over R plus 1 times X plus 1 over R plus 1 times XD. So depending on the information you're using, the reflux ratio or some ratio of the flow rates, you would determine this line. Now from the problem statement, we're told that we are operating L over V at 1.4 times L over V min. So we don't know what this minimum ratio is, but we do know how we could calculate that. Whenever we have a minimum ratio of liquid being sent back into the distillation column, we know that that minimum flow rate is going to be correlated with needing an infinite amount of equilibrium stages to achieve the separation we're doing. And so we go back to our XY diagram, and I'm going to draw our 0.95 liquid mole fraction point. This is our XD, what we're looking to get from our separation. To get an infinite amount of stages, we know that the operating line for both the feed and the rectifying section have to intersect. If we draw this line through our highest point of our feed equilibrium intersection there, then we're going to get a pinch point at that location, and that pinch point is associated with needing an infinite amount of stages. And I'll show you what I mean by this, or it'll make sense as we start doing this more. So now that I have these 2 points, you would want to determine the slope of a line through them. Now the reason that this is our L over V min is, again, recall that the equation for our operating line in this section has the following form, and the slope is L over V. So by drawing this line that is associated with infinite stages in minimum reflux, we could determine that now our L over V that we're actually operating at is 1.4 times that value, which gives me a new slope, 0.868. So I'm going to use 0.87, and now I could determine my operating line for the rectifying section as 0.87x plus D over V times our distillate composition. So we know our distillate composition is 0.95. We don't know what D is. However, we do know that V is equal to the liquid going back into the column plus our distillate leaving the column. Therefore, if dividing everything by V, we could see that 1 is equal to L over V plus D over V, which allows us to substitute in 1 minus L over V in place for D over V. And so when I do that, I get 0.13 times 0.95, we get 0.12. So now we have our operating line for our rectifying section that we could add to the McCabe-Thiele plot. So we know the intercept is around 0.12, just about the closest I could draw on this. We're going to make a line that goes through these 2 points, and that is our rectifying line. So the last line we need to add to our plot is that for the stripping section. And now that we have 2 of our operating lines, we know that the stripping operating line must also coincide with an intersection at these points, and we see an intersection between our feed line and our rectifying line here. The other point we know is that the bottom's composition is 0.05, which falls on our XY line. So we can just draw a line between these 2 points to determine our stripping line. So I like cleaning up the plot. We don't need our rectifying line going all the way into our y-axis. We also don't need our feed line going past our intersection point. And that leaves us with a cleaned up McCabe-Thiele diagram. So we successfully plotted our operating lines, and in another screencast we'll work through determining the equilibrium stages and the molar flow rates that we were asked to in the problem.